Hi everyone, my name is Michael and I'm working for Hibernating Rhinos, and this is not a very well-known company, but we are making one of our main products is a document database. Okay, so I'm going now to tell you a little bit of the lessons learned that I learned for the last 5 years working in the company. And as you can well understand and assume that the database is something that is very resource intensive and it's a good place to see and experiment with performance and see how performance affects day-to-day operations. Okay. This database is written in C#, in .NET, but for all intents and purposes, any language that is garbage collected, I believe what I'm going now to tell, at least somewhat relevant. Okay. So memory and memory management. In any language that is garbage collected and managed in a VM such as Java or .NET, memory is usually something area unexplored. Like in ancient times, you would have maps with unexplored areas where cartographers would write, here be dragons, because there is something scary and unknown there, and people tend to be scared of unknown and imagine dragons. So usually developers in .NET do not think too much about memory. It's there, it works, it's nice. And garbage collector can be very nice for developers. Productivity, you just work with it. You do not need to manage to allocate, to deallocate, to think about where you allocated to the reference. It's just there, right? No pointer accounting like you would have in languages such as C++. And then, as a consequence, you don't need to deal with memory-related issues. You don't have buffer overflows. You don't have, at least not if it's not a bug in VM, but that's another story. You don't have stuff like memory leaks. You don't have to hunt for memory-related bugs. It's nice, right? But I have found over time that a garbage collector can be your worst enemy if you're not careful enough. And what do I mean by this? Take a look at this very nice screenshot of a profiler. This is a profiler screenshot of not very heavy operation, and you can see that the application spent about 61% of its time just waiting for garbage collector to do its thing. So why? It is something that I was really baffled when I saw this the first time, because garbage collector is supposed to be some magical thingy that just makes your unused memory disappear, right? So let's try to understand, before we understand why, let's try to understand what the hell is memory management in .NET. So memory management or managed heap can be thought conceptually as two, I would say, modules: allocator and garbage collector. Allocator in .NET is a very curious thing. It's not a simple algorithm, I would say. Its allocations are very cheap. Actually, you get managed heaps, you get some sort of pointer that each time you allocate, it just increments. So allocations are very cheap. And when you have not enough memory, what you do, you ask for more, right? Oh, here comes the interesting part. Allocator can call and cause a garbage collector. So let's take a bit closer look about what garbage collector does. When you use in each and any .NET application, you have a graph of references between objects. And when you allocate an object, it gets assigned a generation. Each time a garbage collector runs, it goes over this graph of references and sees what object is unreachable. This means it's unused, right? So you can imagine that traversing a graph with billions of objects can be something not trivial, to say the least. And one of the, I would say, performance optimization Microsoft did is assigning a generation. So each time an object survives the garbage collection, it increments in generation, and each subsequent generation has less frequent garbage collection. So it makes sense, because if your object is still usable, so maybe it will be used a bit longer. Kind of a trade-off, I would say, between memory usage and the performance of a garbage collector. Now, another thing garbage collector does, it's just called compaction. So it compacts the holes that you have when you free memory. So it does also a bunch of memory copies, which is a very nice but linear operation. Large object heap, LOH, is when your object has more than 85 kilobytes. This means that it gets placed in large object heap, and there the compactions will not happen unless you specifically ask for it. So, courtesy of .NET 4.5, you can explicitly ask for compactions in large object heap. This decision is pretty logical to me, because constantly copying large objects in order to compact is kind of a waste usually. Now, another thing, in order to understand what this garbage collection is, when it triggers. So it can trigger either when there is a lot of fragmentation in memory, or when the allocations reach a certain threshold. And this threshold depends on the way you allocate your object mainly. It's less important why it does. It's more important that the more you allocate, the more chances that you will have garbage collections, right? So what can we do? We can start from very simple thing. We can just allocate as less as possible and make objects to live longer, right? Because less garbage collector work we can have, less pauses we can have in our application. And the pauses, the most annoying thing with garbage collection pauses, they're not deterministic. So you cannot even predict how can they and when they can happen. Now, another thing I found that when you deal with strings, when you deal with lots of collections, this is something that you frequently want to treat and address a part of a string, part of a collection. So you can either write something yourself or use nice Microsoft constructs, such as array segments, string segments. And those constructs allows us, for example, to address a substring. String segment allows us to address a substring without allocating this memory for this substring. And what is important, I'll touch this subject again a bit later. Strings in .NET are immutable. So this means whenever you want to address a substring by the regular syntax of C#, you will do allocation. Each time you do string concatenation, you will still do allocation. And allocations, as we have seen, can have some pretty big consequences, assuming your application is something that is heavy. And from what I've seen, any non-trivial application requires some resources and some CPU to function properly. Also, we can do some recycling, which is object pooling and caching and all those things, which might seem sometimes unnecessary, but again, in a hot path, a properly cached values can be a very good boost to performance. So this might seem trivial, but still less work for garbage collection is more performance, right? But I will tell you now that we can do more and we can do better than this. So I introduce you the 3 types of .NET memory that you can have and use in .NET. It's not exactly .NET memory, but it's the types of memory that you can use. Managed heap, we all know and use. It's when you just call the nice constructor syntax. Or to be more exact, nice new keyword. And you get memory from managed heap. That's nice. But what is a stack memory? When you define a function and run a function, each function has some area in memory which is used for internal purposes. Those purposes mainly are used for internal .NET means, such as in order to understand what are those means, for example, when you call a method from another method in .NET, the parameters of this method are pushed to a local stack of that method and then called. This is called stack-based calling convention, if I'm not mistaken. So each method in .NET, what's important, each method in .NET has a stack. So why use this memory? Very simple. First of all, you avoid garbage collection here. Each time you allocate on the stack, it will get automatically and most important deterministically freed at the end of the method. Now there are some trade-offs of this, of course. So first of all, you can use primitives only because it is not designed to hold complex objects. It's also small enough. It has a limit of 1 megabyte. 1 megabyte. So if you use more, you will get very nice Stack Overflow exception, which everyone likes, I suppose. And such memory can make your garbage collector a bit happier. Now, don't catch me on this implementation detail because .NET Core and .NET now are open source, .NET Core more exactly. So according to language specification, where this stack memory lies, whether it's part of a memory that's allocated for the method or something else, it's implementation based of .NET. So there is no clear set specification. Where should it be in the specification of .NET specs? Now let's see an example because this may sound like a bit theoretical. Consider the following code. Let's assume we have a list of orders in memory and each order has a status. And we want to do something very simple. We want to see which status is the most numerous in all orders, so which is most frequent, right? So let's take a look at the first attempt. So we can just use link and we just do group by, then we do select, where we transform, do count. Sounds very readable, very nice, right? But take a look at how many allocations we have here. Each time you use a delegate, you allocate memory. Each time you use new with anonymous object to allocate memory, lots of allocations. Okay, but at least it's readable, right? Now maybe we can do better. It's lots of allocation, maybe we can do better. Take a minute to look at this, what happens here. How many allocations do you think we have here? We have only one, right? So we essentially are doing what we used to do before link came out, or if you're programming Java, this is something you don't see link, so I assume, I'm not a Java guy, but I assume you are doing this, something similar in such cases now also. But notice that we have one heap allocation. Then we just go through arrays. It is a pretty trivial code. We go through all the items and we just count and then we select the largest occurrence. So, and then we use the same code. Can you notice the difference? Okay, raise the hands who noticed the difference already. Very fast, right? So this is actually a C# keyword called stack alloc, and um, we have allocated memory on the stack. Looks very insignificant, right? Insignificant change. So raise hands who thinks the link version will be most performant. Okay. And who thinks version 2 will be most performant? Raise hands. Okay, and this version? Oh, great. So you are correct. Yeah, I was kind of leading to it, so it's no brainer. This is actually a nice project called benchmark.net. I like this project very much. This project does micro benchmarking on a single method and can track lots of very nice statistics about how method is executed. So you can see that the link itself, you can see here that min column is the total time of execution of the method. You see the link is not very effective because you need to parse all sorts of expression trees, the delegates, you need to compile those in memory and do all sorts of evil stuff that link does in order to be readable and very nice. Now you can see that between stack allocation version and heap allocation version with the array, there is not very big change in the running time, but if you look at the two rightmost columns with gen 0 and allocated, you can see that link allocated 2 orders of magnitude more memory than the array, and stack allocation allocated 0 memory. 4 kilobytes at the worst scenario might not seem like much, but if you consider what happens at the hot paths and billions of executions of very commonly used methods, each such allocation, as we have seen before, can cause a garbage collection. And garbage collector is not really selective type of thing. It just goes and goes until it goes all over your graph of references. So the more you avoid allocations, I would say it's a bit better. Now, let's talk about unmanaged heap. Or unmanaged memory. This is something that is usually not used in .NET. In my opinion, it's a shame more people don't use it because it's actually much easier than you might think. When you use unmanaged memory, you have the control, right? So the allocations freeing, I lamented before that is not deterministic and garbage collector. The unmanaged memory is nice because you can just, you know your domain problem. You, as a developer, you know when you should free memory, when you shouldn't. You can know when your application has idle time. You can track all those things, and you can just decide how and when you can allocate and deallocate memory. Now, not all allocation algorithms are born the same. So you can also tailor your complexity of allocations and allocation algorithms to be fitting your specific types of problems. So for example, in RavenDB, we use several custom memory allocators for hot paths. So each custom allocator is designed to solve specific problem in specific area of the application. So there is no one true way of doing those kind of things. But still, what I said until now, it's a bit abstract. So let's take a look at some nice and simple example. So we see here very simple method that traverses a string. That's nice, but if we look closer, you can see several allocations. As I said before, string is something immutable. So each time we change a string, each time you do something in .NET for strings, you just need to allocate more memory from heap. And as you might have guessed now, we can do better than this. Here we have iterative way of reversing a string. We just go through the string backwards and just copy to the destination string the characters and backwards. Nothing very complicated. But you can see that we have two allocations here. We can do better than this. Now we will take a look at this a bit longer time than previous examples, because I believe there's some unknown syntax will be here. So this method, functionality-wise, does, and the idea of this method is the same this previous, with one small change. We have fixed char pointer to a string and the destination string. What is it? What does it is actually a C# syntax, which is not a new syntax. I believe it's either .NET 2 or .NET 3.5. Not sure, but it's not very new syntax. What it does in the scope of fixed, it prevents from garbage collector to moving and compacting your value, so you can safely acquire a pointer. One of the reasons in .NET you usually, without using special syntax, cannot acquire a pointer, because garbage collector can move your heap values from place to place when it's compacting them. So if the syntax would just allow to take a pointer, the pointer might, without any notice, because garbage collection can happen without any user intervention, just become invalid. So there is special syntax to acquire pointer to a managed object. Now we acquire two pointers and do exactly the same thing. And as you can notice, we have managed to go down to one allocation. This example, I don't believe it's very difficult. So even with small things, when you want to optimize them for hot paths, you can do much better things. So let's do this small voting again. Please raise a hand who thinks that the first variant will be most performant. No one? Okay, the second. Okay, you understood my trick. I'm too transparent. So let's take a look at the results. As we can see, it's not exactly link, but the first attempt was not very heavy, but we didn't do too much there, so it's not surprising. Well, as you can see, unmanaged and managed memory variants, their running time is almost the same. You can also see that a tiny little bit, the unsafe variant was a tiny little bit longer. It depends on the fluctuations, but the more important thing, you can see that the regular, I would call it this way, the regular day-to-day implementation of string reverse is also fluctuates more, as you can see in the error column. So, but the most important thing is allocations. As you can see that the unsafe implementation did significantly less allocations than the trivial one, and even the not so trivial one, if you can call for loop with string not so trivial, but anyway. So as you can see, unsafe and stuck allocations can be very can bring lots of benefits to preventing garbage collection, or at least lessening it somewhat. So now comes the question, so okay, stuck allocations is something relatively simple to use because it's part of .NET, but what do I do with unmanaged memory? Well, you use correct memory allocators. And we'll now going to talk a little bit about memory allocators, because it might seem that a memory allocator is something computer sciencey and very difficult and very complex, but it's not really. It's something it's relatively simple idea, and there are many algorithms for memory allocations which are pretty trivial and simple to understand and use, and they're still effective. Okay. So what is a memory allocator? It's, as I said before, an algorithm or a way to manage free memory, allocate, and free memory. And the first thing we should remember when we are dealing with memory allocations, and memory allocators to be more exact, that allocating and freeing memory is not immediate, is not simple, does not, maybe in some cases it is, but if we're talking about big O notation, it's not always O1. In some cases, it can be logarithmic complexity or more, depending on the memory allocation, and I mean both for allocating and for freeing. So essentially, we're talking about allocation strategy, right? So let's see more concrete example, the free example. The most trivial memory allocator I can think about, it's usually called monotonic or arena allocator. It's something very simple. You allocate equally sized chunks of memory, right? And then you hold a pointer to a next free segment that you can allocate. Very similar to what .NET Allocator does actually. But instead of freeing like a .NET Allocator does and tracking references, the idea here that you do not free everything at once when you don't need, when you don't need the memory again, you just free everything at once. So for example, in our database, we are using arena allocators for short operations like a web request. We don't need to do anything much. So we have a context, an idea in RavenDB called a operation context. So operation context allocates some memory which can be used for this specific operation, right? And then it just allocates. We don't need to free because there is essentially very short-lived operation. When the operation starts, we just return this memory again to whatever pool, and we have pooling of those operation contexts. So the whole scheme can be very efficient because you have, if you are using big O notation, O1 allocation, and essentially free in terms of performance, freeing of the memory, right? Now, what if we need some more long-lived allocation? So there is a memory, sometimes it's called multipool, sometimes it's called free list. The idea here is that you pre-allocate many memory blocks of certain sizes which are powers of 2, and then you maintain a linked list of such objects. Now, whenever you need to allocate, you just, let's say you need to allocate 6 kilobytes of memory, so you just allocate the closest power of 2, which is larger than your value, and if you need to allocate 6 kilobytes, we allocate a block of 8 kilobytes, and we just take from the end of this list, or when we free, we add to the end of the list. And in this way, we have allocation, and the allocation, depending on how you store the list, you can do it even in close to amortized O1 complexity if you store the headers of such linked lists as a hash map or something similar. Now, memory allocators can be a bit more complex than this, because the downside of the standard, I would call it standard multipool allocator, is that you have some memory waste. You waste some memory because you, when you want to have something like 9 kilobytes of memory, you allocate 16 kilobytes of memory. So this is something that is called a body allocator. Body allocator is a very interesting idea that when I saw it the first time, it took me a bit to understand. So, but the idea, in my opinion, is very elegant. you have, let's say you have 256 kilobytes of memory that you want to allocate for some reasons. So you either allocate all of it, but if you want to allocate part of it, you divide it recursively into smaller but equal sized chunks. And then let's say you allocated several 64-bit chunks, 64 kilobyte chunks, and then you free one of them. Why body? Because you but you check the sibling leaf of such tree. You can look at the memory free list of such allocator as a tree. You look at the sibling, so it's called body when this allocator is described, and see if it's also free. Then you mark their parent as free as well. So if, for example, I had 64 kilobyte chunk allocated and the other one is free, and I'm freeing this allocator, so until it's freed, 128 kilobyte is marked as taken because part of it is taken as well, right? So in this way, we can lessen the memory usage of a system by wasting less memory, basically. Yeah. What? How? Okay, maybe the camera didn't see that. How the question was how deep this tree can become. It depends on what you need, and usually you just in practice you just experiment with it until you find the proper complexity, not complexity, but running time that is fit for your problem. So there is no, as I said, no one true way of doing things. This is an algorithm. You just need to fit it to your problem domain, basically. By the way, if anyone has questions, I like questions. So feel free to interrupt me and ask questions. You don't need just to listen. I'm happy when people ask questions, really. Now, to sum it up, when you are looking for a memory allocation algorithm, the first thing you should look at how and in what way it stores its free space. So free space management is crucial. From free space, you can derive its complexity for allocation and deallocation, or freeing. And then there is something that's my personal term, I'm not sure how it should be called, maintenance routines such as compaction in .NET memory allocator. There are some algorithms that might have such compactions which are part of allocation or free operations or not. For example, the body allocation, what I call memory maintenance routine, is essentially checking whether the sibling node is free or not. So the maintenance routine might add to a complexity of allocation or free operation, or they might introduce some non-deterministic poses like a .NET allocator does. In short, there is no silver bullet. I am not sure who said that and whom I am quoting, but there is no silver bullet. So what I want to encourage you to think about those things, such as memory allocation and how to use memory and where to use this, because obviously implementing memory allocators, implementing different strategies and optimizing for memory and garbage collection can cost money and effort of developers is money and time. So there is a need to find a good trade-off. At our company, we usually profile for hot paths, and then we optimize those hot paths. Now, let's see, that's nice, but let's see concrete effects of such optimization. And I am now going to show you results that I did with previous version, which did not have any of such optimization, and current version, which should be released, I think, in about a month. that I did on my dev machine, and my dev machine is not particularly performant or strong. i7 CPU, 60 gigabyte of RAMs, and not really fast SSD. Pretty slow SSD, as my colleagues can, which are sitting in the background, can attest. And I was importing million documents because it's a document database. I was importing million documents into the database. So this is a total running time. You can see that after optimizations, we almost 3 times faster than unoptimized without such optimizations of memory, right? But I was talking not about running time, I was about talking about garbage collections. So let's take a look at this and notice that previous version was waiting for 63% of the running time of total import time. It was waiting for a garbage collection, and the optimized next version does not wait at all. Zero waiting time. You can see only background garbage collection happening. Now, if we take a look at more specific breakdown, you can see that we had only generation 2 objects in the optimized and the next optimized version, which are long-lived, and we have all sorts of objects because when we wrote the previous version, we didn't care too much about the performance of this kind. Now comes the question: when you have use such techniques as unmanaged and use unmanaged memory, there coming the issues. So I'm going now to talk a little bit about how you can deal with additional issues which sooner or later will surface if you use unmanaged memory. Now, the first, it's a trick that was used in implementation of, if I'm not mistaken, one of the Linux kernels to find memory leaks and more, no, it's not memory leaks, actually, it's buffer overruns when you address memory which you should not use. It's called electric fence. What we see here is a pinvoke in Win32 API. If you are Java people or Linux people, there are similar functions for POSIX API, so the only thing that would change here is the name of the pinvoke that we use. And the general idea is that we create for debugging when you have some access violation exceptions in Windows or segment faults in Linux, you create custom memory allocator that just allocates what we see in the green, allocates the memory that you actually use and protects or allocates a read-only memory that you should not write and the system will cause you to fail, right? Allocates from the both sides of the buffer. And in this way, if you do this little padding of read-only memory on the both sides of the buffer in debug mode, you can catch, as I have needed to do such hunting, I've done such hunting several times, you can catch very fast where your actual buffer overruns happen because you fail at the same specific place that the buffer overrun happens because of the read-only memory. Now, there is another trick that is not really a new one. Anyone who ever dealt with C++ probably heard about this one before, or COM objects special. This is a reference counting. The idea is that when you pass your allocated memory segment to another object, you increase its reference count. In this way, you can track how many references, and this means how many, usages you have of this particular memory. So you can do all sorts of things of it. For example, you can track if you have a pool of, if you have pool of such segments, you can track which segment is used twice, for example, or if you can track which segment is used after it's supposed to be freed, stuff like that. right? So it's a very simple but very powerful idea. And actually, in C++, there is something called smart pointers. So the idea in C++ of smart pointers is something that you allocate and it tracks its own usage and gets freed automatically. So some of smart pointer implementations actually use reference counting. If I'm not mistaken, it's auto pointer, but don't catch me on that. I'm not a C++ guy. And then there is another nice trick that you can use. Since even if you are using unmanaged memory, doesn't mean that you should not use C# features such as destructors, or to be more exact, not destructors but finalizers. So this is something also that we do in our RevNDB implementations. We count references and then we output debug messages. Of course, when it's in compiling for debug, we output debug messages if something that wasn't released properly. So in this way, we are able to catch pretty much all memory leaks that we had until now. So to sum it up, with great power of avoiding garbage collection, you can get great responsibility. So garbage collector can be really nice, and you should use it when there is no any or managed heap when there is no concern about performance, because again it simplifies your life as developer greatly, as it simplifies mine. But sometimes, and in some cases, when you have very heavy parts of application which should be scalable or should be performant, garbage collection can ruin your day basically. So unmanaged memory is maybe, I thought so myself, so maybe some of you think the same, that unmanaged memory is hard to understand, and it can lead to lots of trouble, but actually if approached properly, unmanaged memory is something very nice and can lead to very, very efficient code. And if you're curious, I invite you to take a look at our implementation on GitHub. The low-level storage looks more like C++ than C#, but our database is C#. So we use extensively unmanaged code and unmanaged allocations, and we use this very successfully. Our database. Okay, I'm not going to do a marketing pitch. Forget that. If you are curious, just try and come to your own conclusions. Never mind. And the last I wanted to say that don't use link when you want something to work fast. That's a big no-no in my books. Link is very nice and readable, but it has its costs, like everything in life. And link costs are not trivial. So now that's all I wanted to say. So there is a link on the Sparrow project. This is actually a project where we implement most of our functionality. We have implemented special strings that can be used, that are allocated in unmanaged memory. We have implemented some serialization, deserialization of JSON, which uses unmanaged memory and uses pointer arithmetics to access its properties without needing to deserialize. So looking at those implementations can be a really good illustrations to what I've spoken about right just now. So my personal opinion is really interesting code there, but if you're curious, I invite you to take a look. Okay, so now that's it.